Okay, so um, I'll get things started. This presentation is meant to be a little bit of an introduction to the session, but it's also pretty opinionated. It's rooted in my own work in some ways. If you've been listening and attending the conference so far, this is going to feel sort of the same but slightly different compared to the topics we've covered. And so I'm going to try and emphasize these connections as well between the Earth observation topic and the ocean modeling topic, as well as between the sort of more AI surrogate modeling stuff we learned about yesterday and this. So let's get going. I'm going to talk to you about like 4 different aspects. What I'm going to call general circulation modeling in first. So this is the sort of the big models that we developed to simulate mechanisms in the ocean. Then I'm going to put the emphasis on the data side of things, as a lot of our modeling and science is driven by data. Then I'll focus on the geospatial component in the third part, and talk a little bit about this community building that we're doing here and beyond, which is something that I'm always very interested in. So general circulation modeling, and here I'm looking at the work that's been done in my department, emphasizing 2 specific models, the MIT GCM and Oceananigans, which we're going to hear more about from Simone later today. So these are some of the main contributions that my department has made to the field in terms of ocean modeling. Yeah, that's not it, but I wanted to sort of highlight those 2. The MIT GCM, so on the right-hand side, you have sort of the commit history from those 2 models. MIT GCM, over time, has had 20,000 commits. So that's a pretty sizable effort from our perspective. Oceananigans is slightly less, but catching up quickly. And so you'll notice that the beginning of the time axis is different as well, right? So MIT GCM here I started in 1998. Whereas Oceananigans really started 20 years later, and in a way is a re-implementation of the same numerics with a lot of more innovation, and I would say to a large degree driven by the need to go to GPUs, because that's a technology that really takes our modeling to a brand new speed. So I'm not going to say that much more about these graphs, although I found them kind of fascinating the way they go up and down. I was told yesterday that the sort of tapering down that you see in the Oceananigans side has to do with the use of squash commits as opposed to a reduction in number of effort. So it's just more code for less commits in a way. But I'll say one thing, which is like most of the people here, when we do these sort of things as scientists, we're really driven by the question the science we are trying to address is typically funded that way. And so we are kind of doing this on the side. So it's a lot of effort done on the side. And sometimes we kind of keep it quiet too, because our agencies are not always fond of us doing infrastructure work. So we're all kind of on the same boat. And I would say we are very indebted to this community as well in terms of the architecture infrastructure development on geo side and the files. All right, enough on this slide. This is some of my stuff more specifically. So one of the things I did is we have the MIT GCM, which is one of the most widely used and very useful model out there. I wanted to be able to integrate that into my Julia work, so I developed this interface called MIT GCM GL that now I can use to both pilot and interact with the model runs, and as well use to analyze the results. So with MIT GCM GL, essentially I can forget about the fact that MIT GCM is in Fortran and operated through text files and shell scripting and stuff like that normally. But it's also, in my mind, a way to have MIT GCM in Julia already and make myself ready for when shenanigans can become the workhorse for my sort of workflows. So that's why on the left-hand side, there is what I call climate models GL, which is a generalization of this kind of concepts. So now I have a list of different models in this that are in whatever language, really, and that I can operate in a standard, simple way, interactively from Julia. With the notion that, again, when I want to use MIT-GCM or shenanigans, it's just like sliding for the other, right? So I'll tell you more about this in my later presentation. One of the things that I love about Julia is the interactivity it provides. So I wanted to emphasize that. In many ways, this effort to move MIT-GCM to Julia opens a whole new way of doing modeling. So on the right-hand side is the Julia RUPL version of what it takes to do like a multi-decadal simulation of MIT-GCM today. And on the left is the Pluto.gl interface. So Pluto is a notebook framework that some of you know. We will use it this afternoon. It is reactive, meaning you end up with a HTML page, and if you click, things just react. So it's not necessarily the way you want to operate gigantic simulations, but it's fantastic for communication and exploration and interactive analysis. So by just writing this little interface to MIT-GCM in Julia, you get all of that for free, which is fantastic. Another line of my research involves simulating ocean circulation and processes not on a grid, as we were talking about before, but following the fluid. And so that's one of, maybe the biggest difference between what the geo community does and what we do in oceanography or in climate science is like, for us, everything is moving all the time and to a first degree. So if you're doing science on land, there's also movements, but they're often neglected, right? It's much more static. So a popular way of framing that and addressing this movement of things is to actually simulate processes along trajectories that follow the fluid. So here are two examples from this Drifters GL package that I created, which lifts the Julia ecosystem for differential equation very directly. So it's a kind of a somewhat thin layer over a beautiful framework that Chris largely participated in creating with his team. And you have two examples on this screen. On the right-hand side is the ocean one, where we're following the Gulf Stream, as you sort of see, or might guess. The colors represent the depth of the particle. This is in 3D. On the left-hand side is another example from the atmosphere. This is based on a simple simulation of the atmosphere by the MIT-GCM, which can also do that. And the dots are the results of the particle tracking algorithm. So this is already an example of these kind of composed workflows with different models that we pile up one after the other, and that I will tell you about later in the second session. Alrighty, before I move on, I want to emphasize one of the very important aspects of ocean modeling today, which is the modeling of the marine ecosystem. So biochemistry, carbon, planktons, the interactions of all of those things together, which play a key role in regulating climate, are also a fascinating scientific topic. If you are looking for PhD topics to explore for the next 20 years, there's plenty there on the biology side. That's kind of a rare thing in a sense. Physics is much more mature. And there's a lot of activity in the Julia community on this. So I've highlighted the two packages that you will find in the Julia Ocean organization. Plankton individuals is an agent-based model that's a hybrid between those two model approaches that I described, gridded or following the flow. IBEX is more of a kind of a algebraic solving for the effect of ocean circulation in a steady state sort of things. So it's a very different perspective. And ocean biome is something I don't know very well, but it's connected to the oceanigans effort. And the one at the bottom, they're not written in Julia, but they're now available in Julia, and this is the so-called Darwin tree model, which my department and the group of Mick Follows and Steph Dukevich in particular have developed, and I would say is today's best and most complex and most interesting ocean biology model out there. So the plot is primary production as a function of the season and as a function of depth. I'm not going to go into the details, but again, with sometimes simple interfaces, we can bring these models right to Julia and bring Julia right to them, right? Do you have any question about this part? Should I continue? All right, I'll carry on. Next up, so data-driven ocean modeling. So this is not new. This is, however, very similar to what folks today do with neural networks. So this is the view from 2015, but it's still kind of the state of the art today at this kind of scale. So it's based in this Fortran model that I already described called MIT-GCM, which has this rather unique property to be differentiable throughout. So if you can think of it as a gigantic, very complex neural network itself, in a sense. What you have on this slide is sort of the ingredients that go into creating what we call an ocean reanalysis, which is a synthesis of all observations collected over decades with dynamics combined to give you the best kind of mechanistic understanding of the way that the ocean is behaving and evolving. I'll show you more details in the next slide, but the box here is the so-called cost function. So that is already familiar if you've looked at some of the discussions yesterday. That is the measure of like overall the misfit between a model solution and a whole set of data sets of data. That is what we end up minimizing by running the MIT-GCM forward. So that is the way we sample sort of the posterior distribution of the data space. And then calculating the cost function, that is the driver of then the backpropagation part, and then we iterate. So very similar to what we were talking about yesterday, although one detail is that every one of those loops takes about 5 days, so we don't necessarily make gazillion samples of the state space, so we tend to think more about how to sample it, even more so than in other cases. Here on the left, you have what I call the control vector space. So these are the adjustable parameters that the optimizer is going to work on. On the right, on this side, you have the data. I'm not going to tell you about all of those things. Everything at the top are what we call in situ observations collected in the fields by ships, by floats, by drifters, by various instruments. A lot of the satellite data is listed in the bottom. And the importance of the satellite data should not be underestimated. That's one of the reasons we are kind of heavily sponsored by NASA, and that these products have become kind of the reference ocean reanalysis that NASA produces at JPL, where Alex works. One thing I'm going to highlight, though, and that's why there are those boxes, is the numbers. So if you look on the left, the vector of the variable, the parameters we adjust automatically with this. These are numbers of 10 to the 6, 10 to the 6, 10 to the 7. The grand total maybe is 10 to the 8 or 10 to the 9. So we're talking about billions of parameters. And the size of the data space is the same. So it's really like a gigantic kind of curve fitting exercise. And we have to think pretty hard about how we represent the covariances and all of those things in there. But otherwise, it's the same as fitting just a simple neural network. In practice, it comes down to the same thing. EcoGL, which is loaded here, is my sort of abstraction of this process so that it can interface with all of the things I do. It's not that much more.
Just to clarify, the source of the size of those numbers comes from
Yeah, it comes from the size of the state vector for the fact that we have initial conditions, and then we have also maps of internal ocean model parameters that represent some parts of the physics we don't know very well, like mixing rates. But also, and the bigger number come from the fact that we try to handle the uncertainties in the atmospheric boundary condition, which is now a time series of atmospheric reanalysis fields. And so these we adjust like every 2 weeks. So we take the size of a 2D space, multiply that by 20 times.
So it's like the interface between the two models, the atmospheric model and the ocean model.
Yeah. Yeah, so that number could be reduced, and in some cases we reduce it a bit. But nevertheless, we're talking about 10 to the 6, 10 to the 7. Yeah. Alrighty. So there's a lot of data, right? I tend to distinguish two sides, like I've already done, gridded data sets and then sparse data sets. Here I have shown 2 examples, and both of them are part of the reason I created the climatology GL package that interfaces with these sort of things. On this side, you're looking at a SST, so sorry, sea surface temperature anomaly. This is how we monitor the warming of the ocean from space the most directly. This is something that you have heard about in recent years because it's reaching new heights. And there is a whole set of scientific questions related to marine heat waves. So this is part of the reason I'm working on this particular data set. What you're looking at is a Pluto notebook that will let you explore this sort of time series, the time series of these data sets, and get a map like this. I'll show it again later. So this is sort of an input to my workflows, whether that's the data-driven modeling I was telling you about or my scientific analysis. On the left-hand side is more about the output of the ocean analysis. So these are time series of ocean transports. One of the things that the ocean does is it takes, say, heat here and it moves it elsewhere. For example, in the Atlantic, with the Gulf Stream, we tend to bring some heat towards the higher latitude, which moderates the climate in Europe. So monitoring and calculating these things precisely is an important scientific goal. And that's one of the reasons that we create this ocean analysis. So this is now also something that in the end I make available, those end results, through climatology GL. For all of the in situ sort of sparse data sets that we collect in the ocean, I've created this ocean robots package. On this side, you have a list of the ones that I've already interfaced with. And a map in the middle shows some of them. So specifically, it shows the Argo profiling floats, positions, and what we call surface drifters, as well as some of the buoys that we have in the tropics on the map. With these things, of course, you can do geospatial statistics, and we'll get to that in a bit. The list on the right-hand side is, most of the main ones are already there, but the idea is to keep building this up. These are fairly complex data sets. And I think with Julia, we are making it much easier to look at them. So I think I'm really excited with that. On the left-hand side, on this side, is the abstract from a paper that I recently published with the JuliaEO proceedings, and it is something that I've presented also at this recently at the Ocean Predict 24 meeting, which took place in Paris in December. So it's titled Digital Twins for Ocean Robots, because the idea really is to bring together the models and the data through these sort of interfaces to enable them from benefiting from one another. So a kind of a two-way interaction framework is what I'm after, which I'm going to emphasize in the coming slides. So here is an Argo flow and its data. The little maps on this side show you the trajectory of this instrument that's been put in the ocean and is able to drift with the current. This one lived for, I think, 4 years. And then along the way, it measures properties going up and down. So these are the plots on that side, which show temperature as a function of time and depth, and salinity as a function of time and depth. The little code snippet is what it takes today for you to generate those plots without nothing else. So there's only 3 lines, the one that activates the packages that I've been talking about, specifically ocean robots and Argo data, and then Karomaki for plotting. Then there is a line that says this variable equals read of an Argo float number 6900900. That's the identifier of that particular instrument. And then the third line is the plotting. There's a little bit hidden underneath, specifically that the read command looks if you already have the file or not, and if not, then it downloads it. And then it reads the netcdf file in memory, processes it, interprets in the vertical on the fly, returns a data structure, which here is called Argo, the result is. And because we've done that, because we have the data now in a data structure that is identified by a type, the plot command can just dispatch and do what it needs to do. Yeah?
Do you have also a way to show a map, a horizontal map of interpretation?
Yes, we have, I guess I'd say we have several. It depends a little bit what you mean, but I think you probably mean, a kind of a gridded interpolated product. So I'll talk a little bit about what I'm doing on that node, which is sort of a kind of a multi-grid geospatial statistics approach, where I'm working on this right now, in fact, where I'm building this kind of maps to simple sample averages at different scales. But I also say that Alex Barth, who is here, has a different set of methods for this, called Diva-ND, and presented this, I think, last year here. So we have several different tools already that go to that. It's a bit more involved than just plotting it, right, in a sense. You kind of need to think about how to interpolate. But yeah, we already are pretty well advanced in that field. All right. So I've told you that I want not only to get the data, but I want to emulate it, right? And so on the right-hand side is one of those, like a simple emulation of these data sets. Everything that I did here is I downloaded the climatology, which is something I created, one of those gridded data products we just talked about, from the web, and that's went through the climatology GL package, and then I interpolated to the point and season of the float, of where the position in time and space of where the instrument was. And as you see, the left-hand side and the right-hand side already look pretty similar, right? And this has to do with the fact that a lot of this signal really is coming from the displacement of the instrument across contrast of temperature and salinity in the ocean that are changing not so drastically that a climatology does a good job. So it's a prototype. Ultimately, we want to have much improved emulators of this kind of data sets. But this is step 1. Here's another such example, now for what's called surface drifters. This is the Gulf of Mexico. On this side, you have the real data. On that side, you have a simulation of that. And here, I did something we just talked about. I took all of the data on the side over there, the far one, made a gridded map of the 2 components of velocities along those trajectories, right? And then I took that, and I passed it to an ODE solver through the Drifters GL package, and I simulated the trajectories. So on the right-hand side is a very simple emulator of what you see on the left, which does suffice to capture the basic flow pattern in this region, which is the so-called loop current. So this is water coming from the tropics, and then it does this kind of loop on average, and then that feeds into the Gulf Stream. Of course, you see that one piece that's missing is the more stochastic component that's in the data, and that's something that I'm interested in working on, of course. But this is, again, a simple prototype. But by having this interface, now we can start learning the turbulent piece.
I just want to clarify, for drifter.jl, is there some kind of parameter estimation that happens before you run the simulation from the real world data, or does the emulator just take initial conditions and then just,
Drifters.jl, that's what it does, yeah, the second part. The estimation of the flow fields is something that happens upstream, no pun intended. So in a different package. So something like climatology.jl is where I would take the data on this side over there and make the average map. Or in some cases, I get like three-dimensional flow fields from a previous estimate or things like that. Ultimately, you can put whatever in it. So it's really just the simulation of the trajectories. All right. A third example that I'm going to skip over briefly, but this is a case for the biology where we're looking at, in this one there was, I used FluxGel, so there's a neural emulator in there. The goal being to predict what chlorophyll experiences. So chlorophyll is the pigmentation of the plankton. It's something that you can measure through optics. And it's one way that we monitor marine ecosystems. It's how green the water is, essentially. And so you can sort of predict that from temperature and other parameters, and this is what this is meant to show. And move on. I want to spend a bit more time on the geospatial analysis side of things. Although, is there any other question on the previous part? All right. So let's make some trouble. So the geospatial components of what we do is familiar, but you're going to see it doesn't always fit in quite exactly with what other folks look at. And we're going to start with these grids that tend to scare people off. So when we do modeling of the ocean and the atmosphere, we use grids that look like what you're seeing in the bottom left panel over there. And there are 3 of them. The very far bottom left, that is in fact what the geospatial community is mostly used to, which I would call a raster. So it's a regular grid of longitude and latitude lines. But it has this thing with the convergence at the pole, which for a lot of numerical methods is not ideal because it imposes some very, very strict conditions that make it very expensive to calculate things. So the community has designed other ways to do the gridding of the Earth. One is the cube sphere, which is the middle panel over there on the left. And that's what people do when they do finite volume or finite differences methods for the atmosphere, for example. Milan, which I think is going to tell us a bit about that tomorrow, uses more of a spectral sort of methods, which comes with different kind of grids. But similarly, it makes life a little harder on the users sometimes, and it is the sort of complexity we get. The one that is the third one, that's what we do for the ocean today. So it's like the middle one, but with a piece of the left one, and we took advantage of the fact that somehow we can, for the ocean, because we have land, we can put the singularities of the grid on land. So we've moved this whole thing, kind of this cube sphere bit up. The panel on the top over there shows you the typical grid scale. So it's all heterogeneous is the message here. So nothing we do is straight lines or isotropic sometimes, but definitely heterogeneous. And then in the end, we want to represent these grids on a computer. So that's where this panel here comes in. So this is how we represent it on a computer, the grid that is. So if I take this and I kind of lay it up on a plane, I get this. Which then we can break into different sub-pieces to make it a little simpler, at least have the same dimensions, like square things. But part of the point of showing you this is when I start doing geospatial analysis, that's the first thing I need to deal with. So I need a data structure that represents these sort of things, abstracts the complexity of it, let me operate it easily, and then interface with everything else. I will highlight the fact that the dimensions, in addition of not being aligned with longitude and latitudes, they shift meaning. So this dimension here, which is third dimension, is kind of like that, but then this is the other dimension that follows that. Not only this, but this first dimension now corresponds to this. So everything is sort of, a bit challenging, but you can abstract it away, and then you deal with it the same way you deal with a normal array. And that's what mesh arrays does. So I figured I'd give you a little more detail on how I deal with this sort of things. So the main features of mesh arrays are to represent these kind of grids. Represent the interaction of different variables, because not only do we have these complicated grids, but the variables are staggered. So the velocity points aren't the same as the temperature points, and so we sort of need to think about all this stuff. And we want to be able to use these kind of models scientifically to make precise calculation of transport. So that's what the bottom left panel illustrates. The first thing I want to do, for example, is how much water or whatever is going between point A and point B on the sphere. Well, to do that, I need to figure out the path along the grid of those U and V points. So that's what the bottom left is. This is just following a great circle, but then mapping that into a grid. The most important thing I need to do, probably, really, is be able to interpolate to give people this output on a regular grid. Because when we start presenting this to our users, well, they're not excited. Even our program managers think, we're making that life hard. Go ahead.
So for the GRACE mission,
Yeah.
we compute everything on mass cons, and so it's a horrible grid like the grid. And we produced a user-friendly product where we grid it in like lat long, so you oversample it, so you don't really lose resolution, but you oversample the data. And the users went up by a factor.
Yeah. No, I'm totally with you on that. We have the same experience, essentially. That's like, we want absolutely to provide the output on the native grid, because with interpolated stuff, you lose the ability to do precise calculations in many ways. But your point is exactly right. The vast majority of users, the first thing they want is something simple to use on a regular grid, and so for us too, it's like absolutely crucial that we do that. Yeah. I should say there's also an example of, other ocean model grids that are worse than any of this, which are what people call unstructured, where not only are they not simple, but they are like hexagonals, like your mass cons probably, and then they concentrate in some regions, so they're like, every time you do something like that, for your user, you just need to think, I'm going to give them an interpolated product that's simple, and that's the entry level.
In Michigan, they were doing the adaptive grid, so the grid changes with each time step.
Yeah, I know. So the interpolation scheme that I've devised for this is what's sort of explained on the right-hand side. I needed kind of my custom interpolation scheme. It represents a lot of the same steps, I think, that other people do. But I did this way back then, and really targeted for my grid. And so it starts with finding the nearest neighbor on the sphere. So I do that part in 3D. So I start by going to like a spherical space. Once I found that point, then I can start zooming in. And so I'm going to figure out what subdomain is that in. I'm calling that a tile. At which point, I do a stereographic projection to the center of the tile so that it goes back to a map 2D space as opposed to being on the sphere. With this, I have a grid cell, and I know which grid cell I'm in, so I have 4 points, but it's not quite a quadrilateral. So I do a tiny bit of analytical algebra to bring it back to a rectangular or square. And at that point, it's very straightforward to do interpolation because it's just like one dimension, the other, and you're done. Go ahead.
So with this package you have, that is conservative limiting for bilateral grids for any type of grid.
Conservative, you mean, what do you mean exactly? Ultimately, yes. I have not tested the conservation really in some way. There's one component to this, which is the way to, I think, do conservation properly is to really like look at polygons and their intersections and all of that. That is something that I have not implemented, but we were talking about this with Milan the other day, and we have the same problems when we couple different components. So it's kind of something we're working on and we'll be there soon.
Yeah, because we want couples, so we need conservative grids.
Yeah, no, it's particularly important when you mix, we're talking about conservation of properties across the sea surface between an atmosphere and an ocean. And so here is you don't want to lose like, half of the heat along the way. And even if you're going to do calculation of ocean heat content, which is the integral of temperature, my recommendation at this point is still go back to the native grid where you know everything, all of the grid scalings, and you're not introducing any errors. Because not only is it complicated in 2D, but in the vertical as well. So when there is land, you can make, So I guess the answer is not quite, but, if you really want conservation, you sort of go back to the native grid, and then soon enough, I think we should have the conservative mapping. Alrighty, and the last thing, which is kind of to highlight the fact that having continent tends to mess you up a little, is how do you do covariance on the sphere, first off, and how do you do that in the presence of, say, this mess, right? And so that's one of the reasons, the way we do that is by, instead of using kind of a running window or something like that, we have a tool that uses diffusion, and you can map diffusion operations into smoothing and scales. And so that's something that is also implemented by MeshOS. And so with all of this, I've already shown you this. One of the things we're able to produce is like those precise estimates of integral quantities, and that complements the interpolated model output that we provide otherwise. And then we do things like that too, right? We have these kind of high resolution models. I'm going to show you this in the video way because that's kind of fun to look at. So this is, a lot of what I've told you before is this data-driven ocean modeling we do. We do that at a 1 degree resolution, meaning like meshes of 100 kilometers. But we run the MIT GCM also at much higher resolution. This is from a simulation that was 4 kilometers in resolution. And so with MeshArrays, I'm able to read this thing in and again interpolate them. Here what I did is I put that on the, after interpolating, I wrapped that around the sphere and I'm playing with it with Mackie. And part of the reason I'm also showing you this is you will notice how rich in features this is. So you're looking at, in this case, I believe this was gradients of temperature. So the ocean, not only everything moves, but there is a ton of different processes at different scales. So it's a very complex medium, right? And this is meant to highlight that, just to make your head explode. I'll show you this part. Oops, can I do that? So this is a static image that I'm just showing you in a loop. This is now if I animate through it. And this is not the temperature like I did before. What I did in this case is these are gradients in sea level, which is a very dynamic quantity that's going to capture some of the internal waves that we were talking about on Monday with Adriana. So you see those beams are generated by the interaction between the tides and the topography. And so these models are run at this sort of very high resolution because we want to study these processes, and it's been used to benchmark satellites, in fact. this one is 4 kilometers. We have a simulation like that at 2 kilometers as well.
I'm curious, what kind of compute is necessary in order to like simulate this whole thing?
Yeah, so I'll start by saying the output from this model is 10 petabytes in terms of volume of the output. I'd say it was run on like 50,000 cores on a big NASA supercomputer, maybe for 3 months, to do like a year and a half of simulation. So we'd love to be able to leverage the ClimaOcean GPU-enabled version of the model to sort of speed that up. This is really the state of the art today, in a way. And we don't do this every day. This was done really as a way to test out a concept for satellites or an instrument that's flying now. And so it's really the state of the art in a sense. Yeah, it's big. I've never run something this big myself. It makes for good movies, though. And so here you see, in addition to those internal waves, I'll just mention this, you see like those big currents, right? So this is the big ocean current that you see that's meandering and going around the Earth. There's turbulence in all sorts of ways that you capture, and so it's a very dynamic thing. All right, enough of the movie. I won't say I'm already running out of time. Just going to back here. So if you like this animation, I have a few more that you can look at on the JuliaEO YouTube channel, which involve some of the simulation of the pathways and those that I just showed. This is where I should really highlight that I love Mackie. All of this was done with it, right? And it's just, I've never done this kind of graphics in MATLAB, personally. I don't know if anybody is able to do something as, I think, pretty as this. So Mackie, in my mind, in addition to Pluto and a lot of other packages, is one of the real strengths of Julia ecosystem. So just want to say that. Very briefly, I'll say one word about bridging communities. And first, I love this meeting, which brings together these slightly different perspectives that are very complementary and give us a chance to interact. I'll give you another example, which was more in my mind about bringing Julia to the community that uses MHDCM. And so this is something we did in the fall. We called it the Hack Week. And you see the attendance here. So it was a ton of fun. And so by having this kind of interface between the MIT-GCM, Fortran world, what we've been doing, and Julia, I was able to sort of bring Julia to this group of people. So this is a list of what I brought. The other folks had like Python stuff and Fortran stuff and so on. I brought a whole bunch of notebooks. And then we did a couple of projects, one with the Drifters package, and one on automatic differentiation, where we started comparing different AD tools. So by that I mean Enzyme, and we also had JAX, PyTorch, and all of that. So I think Julia is making inroads like that. I think we can all do a little piece of this in our own field, in a sense. A lot of them, I think this was their first initiation to Julia, and they were quite happy with it. I had a comment at some point of somebody who was using JAX told me, I'm done with that. We use Enzyme. So that's how I think we make incremental progress in terms of merging the different expertise. I'll stop on that, and I will just show you this slide to tease you on the rest of the session. So we're going to have Alex tell us about training denoising diffusion models. We're going to have Simone tell us about ClimaOcean. I'm really excited to know how far we are. I'll come back and tell you about the way that I'm using all of these things to build like more kind of complex workflows with different steps. And I'll talk a little bit about this idea of the mapping of interpolated data there. And then in the afternoon, we will have 3 hands-on sessions. Again, Alex, Simone, and myself. We'll talk about using RUMs, another ocean model in Fortran from within Julia. maybe it's another of the very popular one, RAMs. Then we will play with shenanigans and ClearMotion with Simone, and we'll go back to this particle tracking thing with myself. We'll have a roundtable at the end, which I'm hoping will be a way to exchange and kind of understand, how can we help you, how can you help us, and just have a sort of an open-ended discussion. Thank you very much, and see you in a bit. If there are any questions, I'm happy to take them. Oh, yeah.
So you mentioned the ED tool Tapana. Is this used for MetaGCM data join, or is it the handlers that join MetaGCM?
Yes, so Tapenade is one of the AD tools indeed. There was a list there. It is now being used with MIT-GCM. A lot of this work is done by the group of my colleague Patrick Hambar at UT Austin, and so he's always kind of pursued open source tools to do this sort of things. So we have several tracks going on where we're looking at enzyme, we're looking at Tapenade, which is the most advanced and almost able to now rival with the proprietary tool that we normally use, which is called TAF. What should I say? I think there's one more that is being really explored. But yes, essentially, it's almost there. Not quite for everything just yet, and the performance is not quite at the level of the proprietary tool that we use. But soon enough, we should have a fully open source adjoint for MIT-GCM, which is kind of the advantage of Tapenade.
Is it important work to work a lot with source-to-source translations? When you have this is the forward code, this is the adjoint bottom source.
Yeah.
I'm wondering if this is something also in the Julia community, where we source-to-source translates Julia code and adjoint code, and we can also easily inspect the joint code and maybe add other things like checkpointing, DB instead.
Yeah, I'm not entirely clear how enzyme works, but I think it's more or less what it does at the kind of LLVM compiling level. Now, that's not necessarily going to be easy to go look at the adjoint code, but I believe in that way there is a source-to-source transformation happening. It is useful to be able to inspect the adjoint code, I'm going to say, in a way that's friendly. And to my standard, that means at least Fortran code I can read, or Julia code I can read. Not sure we're quite there. But I do think, it's very useful for the developers and the users of these things to be able to actually understand what's going on in the adjoint. That's kind of your point.
Well, I think that's a trade-off between mooncake and enzyme, right? So enzyme, yeah, it is a source-to-source translation, but it is done on the LLVM-IR source, right? So it will give you an LLVM-IR source for the item code and intermediate representation. So the LLVM intermediate representation is a representation that the LLVM compiler uses for code that is going to compile before it hits assembly language, right? So it's like an almost assembly language kind of representation, and its transformation is right on that level of the source-to-source transform. And so when you use enzyme, if you want to inspect enzyme's operations, you have to read the LLVM-IR. Now, since Julia uses a lot of LLVM, it might be kind of a weird subcommunity, but there is a decent community of Julia users who are well-versed in reading LLVM-IR, and so that can be a way to kind of inspect the source. But I would say that in general, that's the trade-off that you're making with LLVM or with enzyme. That enzyme ends up being faster than a lot of the tooling that you have from a lot of the prior Fortran tools because it specifically is relying on running after some compiler passes, and it's only allowed to do that because it's using the same IR as the compiler transforms, right? The alternative to this is to do something similar to enzyme before you hit the LLVM lowering phase, which is being done by something called mooncake, right? So mooncake is a new AD engine that is being implemented in Julia directly through the compiler passes of Julia's compiler, and because it's being done on the Julia lower level, it's still not necessarily Julia code, but it's lower Julia, which is the same level that
read legible Julia code. And so that has the advantage of being able to be more legible in terms of the source code it's generating, but because it runs before compiler optimizations, there are certain codes for which it's not able to hit the optimal form, and so it has more of the performance of Taconauts rather than the performance of Enzyme for those cases for which post optimizations are not able to be done.
So for those online, I think Mooncake is the name. Is a new development in Julia that is going to allow us to bridge between sort of the user-readable code by anybody and what Enzyme does. That's the summary. Thank you for that. It's very interesting to know. All right,